Hello everyone, my name is Prabhanjan Ananth. I'm from UC Santa Barbara. I'm going to talk about secure software leasing and implications for quantum copy protection and obfuscation. This is a joint talk with Gorjan Alagic from University of Maryland, Zvika Brakerski from Weizmann Institute of Science, Yfke Dulek from CWI and QuSoft, Rolando Placa from MIT, and Christian Schaffner from University of Amsterdam and QuSoft. This is going to be a merge talk of two papers. The first paper is titled Impossibility of Quantum Virtual Black Box Obfuscation of Classical Circuits by Alagic, Brakerski, Dulek, and Schaffner. And the second paper is titled Secure Software Leasing by myself and La Placa. The quantum no-cloning theorem has been used as a basis in designing many interesting cryptographic primitives. Primitives such as quantum money, which allows for a bank to manufacture a money state in such a way that a user will not be able to come up with a different copy of this money state that also passes some verification checks. And then there is a primitive of quantum copy protection introduced by Aronson. I'm going to be talking about this primitive soon. And then there are primitives that talk about the no-cloning property in the context of encryption schemes. They essentially say that an adversary given an encryption of a message should not be able to come up with another ciphertext that encrypts the same message. Right? So the ciphertext will be modeled as a quantum state. And then there are primitives that talk about the no-cloning property in the context of signature schemes. The problem we want to tackle today is the problem of software piracy. So software vendors spend a lot of resources in designing proprietary software, and they rely upon the sales of this proprietary software for their revenue. So they want to make sure that the users to whom they are selling the software to will not illegally distribute the software to other users for profit. So this is the problem we want to solve. So how do we represent software? If we represent software in terms of like a Boolean representation, then the problem is that this can always be copied. So the users can illegally distribute this software to other users, and there's no way to prevent it. Now the question is that what if the software was modeled as a quantum state? So now can we somehow use the fact that quantum states generally cannot be copied in order to solve the problem of software piracy? This is not a new problem. This problem has already been looked at in the quantum community. Aronson, in this seminal work, introduced the notion of quantum copy protection as a solution for preventing software piracy. So what is copy protection? Informally speaking, copy protection has two guarantees. One is functionality. The vendor should be able to use this primitive in order to copy protect the software, and should be able to send the copy protected software to the user. Okay, so even after copy protecting, the software should still retain the same functionality as before. And in terms of security, what we want is that the user, after receiving this copy protected software, should not be able to redistribute the software to other people. This is the unknowability property associated with the scheme. Let's look at this notion in a bit more detail. Suppose, let's say we have a company like Microsoft who wants to copy protect a circuit C. So let's stick to classical circuits for now. So what Microsoft is going to do is it's going to run the copy protection algorithm on the circuit C to obtain a quantum state denoted by rho C. In addition, it also manufactures this evaluation algorithm called eval. So it's going to send eval and rho C to the user. So using this state rho C and eval, the user will be able to obtain the output of the original circuit C on any input. Right? So suppose, let's say it wants to evaluate on input X, it will run eval algorithm, which is modeled as a quantum circuit, on input rho C and X, and the output of this is going to be C of x. So this is the functionality aspect. In terms of security, what we want is that we don't want a rogue user to be able to sort of take the state it obtained from Microsoft and produce two copies of the state, let's say row C1 and row C2, and each of these states are associated with their own evaluation algorithms. We don't want the user to produce these two states in such a way that both these two states compute the original circuit C. We don't want the guarantee that eval1 of row C1 compute C and also eval2 of row C2 compute C. This event should happen with very small probability. So as written here, we are only considering product states. This is not a necessity. This is only for ease of presentation. The user can very well output entangled states. Defining that is a little more tricky in that context. And moreover, we can also consider a general notion as defined by Aronson, where the user can actually obtain many copies of the software, and it's also allowed to obtain many more copies of the software, right? And not just two. The primitive of quantum copy protection is very powerful. It implies a few interesting cryptographic unclonable primitives. More prominently, it implies the primitive of publicly verifiable quantum money. So what do we know about constructing copy protection? There aren't that many works that construct this primitive. They can sort of be roughly classified into two categories. Either we have constructions in the Oracle model, or there are heuristic constructions for very simple class of functions in the plain model. Right? By plain model, I just mean the model that where the algorithms don't use any oracles. And by heuristic, I mean that they are not based on any cryptographic assumptions. You just assume that these constructions are secure. There's no security reduction to an assumption. So a natural question that came out of Aronson's work was whether there exists quantum copy protection for all unlearnable functions. So for learnable functions, it's easy to see that this notion doesn't exist. But whether this primitive exists for unlearnable functions was still open. And in this work, we show that in fact there is like a contrived class of unlearnable functions for which you cannot design any quantum copy protection scheme. And this is a conditional result because we base this result on a cryptographic assumption. So we show that there doesn't exist quantum copy protection for all unlearnable functions, and we base this result on quantum hardness of learning with errors. Learning with errors is an assumption used to base the security of many cryptographic constructions. And we believe that this assumption is secure even against quantum polynomial time algorithms. So to show the impossibility result, what we do is we identify a class of functions such that this class of functions is quantum unlearnable, meaning that any QPT algorithm with Oracle access to this function will not be able to come up with a physical description of this function. On the other hand, if the adversary receives a state that computes this function, then we will come up with an adversary who will output many states that compute the same function as the one associated with the state it received as input. So our impossibility result has implications to another very well-studied notion called program obfuscation. So what is program obfuscation? It's just like copy protection, it's also a compiler. Given a circuit, it produces another circuit that is functionally equivalent to the original circuit. But in terms of security, what obfuscation says is that if I give you this compiled circuit C, then it should hide the implementation details of the original circuit. So this might sound a little vague. I'm going to formalize what this means soon. The notion of obfuscation has had powerful implications in other areas of cryptography, such as secure multi-party computation and functional encryption. But it has also had implications in other areas in theoretical computer science. For instance, it has been used to show hardness of finding Nash equilibrium, lower bounds in differential privacy, and so on. So, a natural question to ask is, whether this primitive is possible. And towards understanding this primitive, let's try to formalize this property a little better. The property what we want is that for any adversary, there should exist a simulator in such a way that the output of the adversary on receiving the obfuscated circuit, the physical description of this obfuscated circuit, should be indistinguishable from a simulator, output distribution of a simulator, who only receives oracle access to this circuit. So in other words, what it is saying is that having physical description to the obfuscated circuit should be sort of equivalent to having oracle access to this circuit. So we are interested in a quantum version of this property, which is called as quantum virtual black box obfuscation. This notion, instead of like transforming a circuit into another, like a classical circuit into another classical circuit, we transform a classical circuit C into a quantum state, denoted by rho C here, with the property that rho C still computes the same circuit as before. And moreover, it satisfies the virtual black box property, which says that having access to this quantum state is the same as having oracle access to this circuit C, okay? Oracle access to the function computing C. So natural question to ask is whether quantum BPP for classical circuits exists, and we show that it doesn't. And even this result is based on the quantum hardness of learning with errors. And in terms of techniques, this result is going to be very similar to the techniques we're going to use to prove the impossibility of quantum copy protection. So prior work by Alagic and Pfefferman had a weak impossibility result. I mean, they only ruled out quantum BPP that transformed quantum circuits into reusable obfuscated states. One such example of reusable obfuscated state could be like a quantum circuit. Okay, so we showed that copy protection is impossible. So now natural question is like, cannot construct copy protection for all unlearnable functions, but can we actually construct copy protection for a subclass of functions, right? And we already know some results in the oracle model, so we can ask whether can we get such a result in the plain model, without using any oracles. And there has been a lot of effort in the last decade to do this, towards resolving this problem. It seems like a very hard problem. We still don't know how to do this, even for very, very simple unlearnable functions, a very, very simple class of unlearnable functions. But instead, what we can do is to realize that there are some settings where weaker notions of copy protection suffices. We don't want the full-fledged power of copy protection in these settings, and so we can ask whether we can design weaker notions of this primitive that suffice for these settings. To understand how this weaker notion of copy protection looks like, recall that in copy protection scheme, the adversary is given the flexibility to produce its own evaluation algorithms. So the adversary produces two states, and each of these states is associated with an evaluation algorithm. But there are some scenarios where the adversary will not have the power to choose its own evaluation algorithms. For instance, suppose let's say there is a specific software that runs on a specific operating system. So of course, the adversary can sort of, by observing different executions of the software, might be able to create an open source version of this software, and might sort of sell this code to other people. But what we want to prevent is the adversary from being able to create copies that run on the same operating system. Microsoft would be okay with creating, so someone creating like open source version of Microsoft Excel, but they would not be okay with someone creating a fake copy of Microsoft Excel that runs on their OS. And to sort of address this setting, where the adversary is sort of more restrictive, we introduce the notion of secure software leasing. In terms of syntax, this notion is the same as copy protection. Microsoft should still be able to sort of lease this circuit to the user in the form of like a quantum state Pro-C and an evaluation algorithm eval. But in terms of security, what we want is that the user should not be able to produce two states, Pro-C1 and Pro-C2, that compute the same circuit C as before with respect to the same evaluation algorithm eval. So unlike a copy protection scheme, the user will not be allowed to produce its own evaluation algorithms. And as before, we want the user to be able to succeed with only very small probability. So we can actually define two notions associated with this scheme. So one is what is called as infinite term lesser security. So in this case, Microsoft leases the software to user, and the user can sort of keep this leased software forever. And we want the guarantee that the adversary, can only produce two identical copies of the circuit with a negligible probability. So another version is a finite term version. In this case, the adversary, after returning back the state, will not be able to produce another state that computes the same function as before. So we construct the stronger notion of infinite term secured software leasing for some subclass of unlearnable functions based on cryptographic assumptions. If you're interested, the class of functions we consider is what is called as compute and compare. As the name suggests, the functions are such that you do some computation and then you compare the output of the computation to something, and based on that you decide to either output 0 or 1. In the remaining time I have, I'm going to focus on the impossibility of copy protection. The main tool in this impossibility result is going to be the tool of quantum fully homomorphic encryption. Roughly speaking, what this primitive allows us to do is, given an encryption of a quantum state and a quantum circuit C, it allows us to efficiently recover an encryption of C of rho. So it allows us to perform computation on the quantum data, even though the quantum data is encrypted. So using quantum fully homomorphic encryption, we are going to construct class of unlearnable circuits that cannot be copy protected. And towards achieving this, the first attempt to use Barak et al.'s technique, which was used in the context of ruling out classical virtual black box obfuscation. Okay, so what is this class of circuits? On input X, this circuit checks if this input is 0, and if so, it outputs encryption of A, where A and B are two values that are associated with C. So on input 0, it outputs encryption of A. On input A, it outputs B, and on all other inputs, it just outputs 0. So one thing I want to point out is that A and B are going to be picked uniformly at random. Okay. So we can show that if A and B are chosen from the uniform distribution, then this there doesn't exist any QPT algorithm with Oracle access to CAB that learns A and B, right? And this can be shown using the adversary method by Ambainis. To show that the copy protection property is violated, we are going to construct an adversary that does the following. This adversary receives as input a unitary U and a state rho C that computes the circuit C, CAB. So it's going to input 0 to to this implementation of CAB, and it gets encryption of A. And then we're going to homomorphically evaluate U on this unitary U on input encryption of A and encryption of rho C. And by the correctness property of the homomorphic encryption scheme, what we will get is the encryption of output of this circuit on input rho C and A, and this is going to be nothing but encryption of state B tensored with rho C prime, where rho C prime is going to be the residual state. Okay. Note that we are sort of stuck here, right? So we neither have A nor we have B. So in order to sort of come up with, in order to break this copy protection scheme, we need to recover A and B in the clear, but we only have encryptions of them, right? So since they're in encrypted form, we need to be able to decrypt them. And in order to decrypt these two values, we are going to use a special purpose obfuscation scheme. This particular notion of obfuscation can actually be based on quantum hardness of learning with errors. And we're going to use this obfuscation to recover B. So we're going to go back and change the class of circuits. So the functionality is as follows. On input 0, it now outputs encryption of A, and it also outputs an obfuscated circuit. This obfuscated circuit is such that it has the decryption key of the homomorphic encryption scheme hardwired inside it. It takes as input encryption of B, and it outputs both A and B. So now let's see why copy protection for this class of circuits doesn't exist. So suppose, let's say we are given an implementation of CAB. So the adversary is going to be the same as before. It's going to obtain encryption of A by feeding in 0 to this implementation. And as before, it's going to obtain encryption of B and some residual state. So earlier we were stuck. We didn't know what to do with encryptions of A and B. But now that we have this obfuscated circuit, we're going to run this obfuscated circuit on encryption of A and encryption of B to recover AB. So, now that we have encryption of A and B, we have the entire functionality of CAB, right? So we can create as many copies of CAB as we want, right? And thus breaking copy protection. Okay, so let me summarize our contributions. We show that copy protection is impossible for a contrived class of unlearnable functions. So we also show that there are weaker notions of copy protection that we call secure software leasing that can be constructed for a non-trivial class of unlearnable functions. I think that the area of copy protection is very exciting, and still there are many questions that are open. For instance, can we come up with other variants of copy protection that might suffice in certain settings? Can we come up with constructions of copy protection for any non-trivial class of circuits? Could even be point functions. We don't know how to come up with constructions in the plain model, right? We only know results in the Oracle model. And even the area of obfuscation is fascinating, and fundamental questions such as whether we can construct quantum indistinguishability obfuscation. Indistinguishability obfuscation is a weaker notion of program obfuscation. For quantum circuits, we still don't know how to do this. for arbitrary class of quantum circuits. So even this is open. So with this, I conclude. Thanks.